Hello everyone. So from now onwards, what we'll do is, so if you see what we have done is, so we have done Python and parallelly we're doing mathematics. So now you are in a good position to understand libraries, okay? Because in Python you'll code, and after that, majority of the times you won't write everything from scratch. So most of the things you'll probably use the code that has been written by somebody, okay? So we'll now study about libraries, okay? And from today I think we'll cover NumPy. So plan is to cover the whole NumPy, and then we'll also look what pandas is, and then we'll see matplotlib, and then we'll see seaborn, and we'll see other things if required, okay? So these are the ML libraries that we'll cover. Okay, the first thing is we'll see what is the library, okay? We'll see what is the library so that we understand everything, okay, in Python. So the first thing is, if you have written code in files, you write these .py files, okay? So you have these files where you write .py extension files. Let's suppose this is the file. When you write these .py files, so if you now have these py files where these Python codes are, so we call them modules, okay? So these .py files where these Python code is, so we call it modules. So let's suppose if I'm writing a, I'm creating a big application. Let's suppose one part in that is calculator. So I'll write a function add. Let's suppose subtract a function will be there, and there will be a lot of functionalities. Okay, this is a module, and then I can create a lot of other modules also. I can create these .py files in which I'll write different modules. I'll name them, and the extension will be .py files, and there'll be this module 2, and let's suppose some other modules, module 3. This is module 1, 2, 3, something like this. Okay, these will be different modules. So what is a module? A Python module contains Python code. Okay, so now if you somehow collect all these modules and put them together and make a wrapper around them, okay, so you call this a library. Okay, so in the simplistic terms, if you see why is this called a library, consider each of these functionality as a book. Okay, and maybe this module is doing something, this module is doing something, this module is doing something. So that's what a book is. So book usually is on a particular topic. Okay, so consider these functions as chapters in the book. Okay, there are different chapters in the book, but all these chapters combined, they form a book. Okay, then let's suppose this is book 1. So in Python terminologies, so one module is like one book. Okay, and then we have second module, that's like another book, but these books are somewhat interrelated. Okay, then we can create a library out of these when we combine all of these modules and put a wrapper, and then we can call different functionalities, so we call it a library. Okay, so library is just a collection of modules. Library, a collection of modules. Okay, and you might have seen, and then they are maintained differently. Like if you have seen, you usually write pip install something. So okay, so this is why they are maintained. You use this pip command to install these libraries. Okay, so these, what is the library now? Library is just this collection of modules, and these modules, they basically contain the Python code. So they contain the Python code. There will be a lots and lots of files. Okay, so and when all of these are put together and made into one thing, that's called as a library. Everybody clear with the libraries? Why are these libraries created now? So it is like if you are designing something, so every time you don't have to reinvent the wheel. Okay, let's suppose you have a car like this. Okay, and then what you have these wheels discovered. You should not do the research again to come up with the wheels. Okay, so better is to use the pre-existing things which are good, and these libraries usually they're optimized. They're written by good coders, and they are optimized. And the big thing is these most of these libraries are open source, and people do contribute, and they have active community where they have this code, and they keep on improving the code, and they keep on adding the new features. Okay, so this is a pre-written code. So this code will be used by some people, and maybe people like you and people like me, we use this code left, right, and center everywhere. So why is this code used? Because it sometimes forms a building block. So as I said, we should not every time reinvent the wheel. So this wheel should not be invented. If wheel is there, we can use, and on top of that we can do something else. That's what these libraries are for. Okay, so now think it like a bag. Okay, to give an analogy, so think it like a bag. This bag contains a lot of stuff. Let's suppose this is a bag. Okay, now maybe you only need a few tools of that bag. You don't need the whole bag. Okay, what you do is in your code, let's suppose you are constructing something, you're doing something physical. By physical I mean, let's suppose you are doing a task in which you want to achieve something, and in this bag we have these tools. What you can do is from this bag you can take tools one by one, and then you can maybe use them here. Okay, but you have to keep the bag somewhere where it's accessible. Okay, that's why these things are to be installed first. If you have to use a library, you should install the things first. So in today's session, what we'll do is we'll use NumPy, and we'll learn about NumPy. Okay, so what is this NumPy? If you see this NumPy, it has two words in it. Okay, NUM and PY. So num means numbers, numerical. Okay, py means Python. So we can just write it numerical Python. As this Python started becoming famous, people started using Python. Okay, and then many other scientific communities also, like people who are doing research, they also started using Python. Okay, and then they felt this Python is very slow. Okay, Python is good in ease of programming, everything is there, but if you come to the computational things, it is really slow. Okay, then what people thought is, people thought, okay, if scientific community is using it and they have to have good efficiency, good speed of these, so why not to just create a library, okay, which will be called as numerical Python, where we'll do these numerical computations, which usually is used by the scientific community, so that it is a bit faster than Python data types. So everything that we can do with NumPy, probably we can do with the lists also. Okay, but these lists are very slow. Okay, and because they are Python objects and a lot of stuff goes into that. But what people have done is they said, okay, let's create something which will be faster than list and which will support these numerical operations. Okay, so this is what they created. Okay, this is an open source library. You can still access it and you can contribute to it. That's what people thought. And the code is written in C. Okay, and this is the code is written in C. That's why it's so fast. That's why we came up with NumPy. So the question would have been, okay, if these lists can do the same thing, why do we use NumPy? As I said, that the Python became famous and scientific community started using it. So when scientific community started using it, people thought, okay, now the Python is good, but it is a bit inefficient. So can we have something which will just remove that thing, which will have ease of programming like Python, but we should be efficient, because scientific computation usually requires efficiency. So that's why these NumPy came from. Okay, now consider this NumPy as a library, consider it as a bag, it has the tools, and now in Python what we do is, if you have to import it, if you have to use it somewhere, we would literally use the statement import. So we'll use the statement import. Okay, we'll say import, and then whatever the library name is, let's suppose it's NumPy, so we'll say import NumPy, and then we'll write some, usually people write as, this is called as alias, as NP. So this is called as alias. So what is this alias? So alias is just a nickname. You can think of it is a nickname, because every time you don't like to name just NumPy, you can just say NP. And let's suppose Mahmood here, you people have nickname. Let's suppose me also, people call me Musa. Okay, my whole name is Musawir, people call me Musa, just as an alias. Okay, so this refers to NumPy. So this is what you usually write. If you see the Python code, there you will see import NumPy as NP. People generally write this. So here, before having this, so it should be there. So this NumPy should be installed. So usually you can just do pip install NumPy. Okay, and then you can even control the versions. Okay, so a different version of the NumPy has different functionalities, and sometimes some things are deprecated and sometimes new functionality are added. So you should also keep in view that whenever you are installing a package, or which we call a library, so you should also see the version, because there's a version control in that, because if something was implemented in a certain way and then people find a better way of that, so they usually upgrade it, and some things might be something might become deprecated, people just remove them and add new functionality. So before installing anything, make sure that you're installing the right version of that. Okay, so this is NumPy, and we'll install it by using pip install NumPy. Let me first share the screen, and so that we can write the code. Give me maybe a second or so. So the first thing that we have to install the NumPy. So we can just see pip install, and then we can say NumPy. Okay, and then you can also say is equal to version, and you can see it requirement already satisfied. We have this because I have created an environment which I named as deep learning. Okay, so now we have it, and so what the first thing that we'll do is we'll import this. So if we have to do anything, we'll import it. So import NumPy as NP. Now we can use this. So if I just run this code, this is test1.py, so I can say Python test1.py. Here nothing will appear because I am just importing. So import is a keyword, and NumPy basically is a library that's installed somewhere, and then I said NP. This is the alias name. So this is how we import these things. So what is this NumPy good for? The first thing is we should see, okay, what is it good for and why should we use it? Okay, now you saw how to import these modules. If you have these libraries or a module, so you can just use import keyword and the module name, and then you can use the alias name. Okay, now what is this NumPy? So as I said, it's for the numerical computation. Okay, so it's basically a library which has these operations which you perform on these numbers. Basically, whatever numeric things you have, you perform the computations. That's what it is good for. Okay, so at its core, there is something which is called as ND array. Okay, if you see, we call that and the object is in the Python. So this is the core thing that we have in Python, that we have in NumPy. Okay, at its core, we have an object that's called as ND array. If you define anything, that's an array in here, and we manipulate these numbers. And by now, you should appreciate everything in computers is a number, and we need to manipulate these numbers. So we should have an efficient way of manipulating these numbers. So now, how to store those numbers? Okay, so how NumPy stores this? It stores them in what is called as ND array. Okay, this is the name. Okay, this is not just an array. It is the name that has been given by the NumPy people who create the inventors of the NumPy. So this is the core object, and this is actually a multi-dimensional array. You can use 1D, 2D, howsoever you want. And now what the functionalities that it has, that these things have fixed size. Okay, they have fixed size. By fixed size, I mean if you see these lists. So these lists basically where you can dynamically expand them. But in here, what you basically do is you have a predetermined size upon the creation. Okay, not like the Python list. And once you want to expand it, what NumPy internally does is it generates a new array. So it generates a new array and discards the other part. Okay, and if you have to basically expand, so this is one of the features of these ND arrays. So this ND array is the core. So now we have a fixed size in that. And the second part is the elements are homogeneous. So what is the meaning of homogeneous? So each of the element has the same data type. Okay, so all the elements within NumPy array must be of the same data type. Ensure that, because it has to give the memory. So if it is of different data types, like the list, and then each of the elements will occupy different spaces and different amount of memory. So here, by giving this homogeneous, so what we ensure is that we'll give the same memory, will allocate the same memory for each element. That's why these are homogeneous. Okay, and you can still, let's suppose if I just generate an array, you can still have string in there, but it will convert all these into strings. Then we'll see it in the example. And then one more thing, because of these things, it does this efficient operations. Okay, it performs efficient operations. And what are the mathematical complex operations are? Because there is a technique called as vectorization. We'll see that what vectorization is. And these are the three important things about these ND arrays. Consider this ND array is the basic core of this NumPy. Okay, NumPy is built upon that. Okay, the core is called as ND array. So ND array, they are of fixed size, they are homogeneous, and there are efficient operations which can be done on that. Let's first see how to now create an NumPy array. Okay, let's go there and let's go to the coding window and see how to create these things. So if you see now, I have done this import NP, import NumPy as NP. So what I can do is I can just create an array. Let's call this array. So this array can be a list 1, 2, 3, 4. Okay, if you just print the type, so I can just say print, I can say type of this array. Okay, if I just print it, obviously this should be of type list. So now Python test, this is of class list. Okay, now what I do is, if I now have to convert this into NumPy array, as I said, the base object, base structure of this NumPy is ND array. So what we can do is, we can say, let's call this N array. Okay, we can say np dot array. So this dot array is a function which will convert this list, so which basically is array. It will convert this into a NumPy ND array. So if you just now print the type, so here you can see this class NumPy dot ND array. Okay, so this is the base structure. This is the core on which we'll build everything. So this is the data structure, ND array. Okay, now you can create, if it's not a list, you can directly create it like this. So let's suppose we don't have this and we want to create an array. So what we can do is, we'll say an array, and then we'll say NumPy dot array, and then we'll create an array like this 1, 2, 3, 4. Okay, so if you now see the type, it will be similar. Okay, so that you have to define this, because if you perform the operations now, I'll just show you an example. So let's suppose if you have this NumPy, if you have two lists, let's call it list 1, say it is 1, 2, 3, 4, something like this, and we have list 2, and let's have that elements 5, 6, 7, 8. Okay, So now if I have to suppose multiply these two lists together, so I'll have to write a for loop, and then I'll have to see, let's suppose I'll just write that for I in a range, or let's suppose length of whatever the length of the list one is. And what I want to do is I want to perform element wise let's say addition or multiplication. Let's suppose multiplication. So what I can do is I can create a new list C. Let's call this new list as C. Okay, C is a list, empty list. Okay, I'll have element wise multiplication and then append them to the list. So what I can do for I in range of list of I, so what I can do is list of one, list of 1 of I multiplied by list of 2 of I. Okay, then what I'll do is I'll append this. So this will be C dot append. Okay, C dot append dot list. This is how I'll do it, and now I can print the C. So if I just uncomment this, if I comment this code, I'll say print C. Okay, now I can just run this file. Hopefully this is the result. So 5 1s 5, 6 2 12, 21 and 32. So this is how I did. Okay, if I did it like this, let's suppose if I did it list 1 multiplied by list 2. Okay, and this obviously should throw an error. Okay, so if I just multiply it like this, so this is throwing an error because multiply is not defined on the list. So what NumPy does is you can do it. So if you just somehow converted this, okay, so let's say we'll have this list. Now we'll say n list in NumPy list 1. This is equal to np dot array, and this is list 1. Okay, and then we have this list 2. Okay, and then we have list 2. What you can do is you can just multiply them. So list 1 multiplied by list 2. So this will do the element wise multiplication, hopefully. Now if I print this, so I'm saying hopefully because I myself don't sometimes have faith on this program. It can do anything, so it is better to be on the safer side. Oops. So now what we can do is do this and comment this out. So I change my directory, probably cd desktop I think we have this. So Python test 1.py. So now if I print this, you can see this should be nlist. Okay, so nlist. Okay, we have to save it also. Now you can see this 5 12 21 and 32. Is it clear? So you saw it just by one operation, and this you can do. Otherwise you have to write this lot of code. Okay, you have to write a lot of code and then do this. Here if you just added this multiplication, you saw that how fast it was. Okay, is it clear? Okay, I can also show you how fast it is. Okay, let me show you how fast it is. If it is clear, let me show you. Let me create a new file. I'll take your questions maybe after a while. So this is code test2.py. I'll show you how fast NumPy is. Okay, then just a list. There is a function called as time it. So the time it should print the time. Let me first check the time it. We write it percentile time it, and do tell me if my voice is not audible, because I fear that this headphone might get disconnected. So this is the function time it. So if I have to time something, I first want to clarify myself. So let's suppose I'm creating a list, call that L, and I'll just use a range function. Let's suppose this range function. So this is 1000 and time it. So what I'm doing is now I'll access each. I'll say each of this raised to power 2. Okay, I2 for I in L. This is what I'm doing. Okay, so there is this problem, but maybe we have to import something to check the time. Let me still run it. I'll see if it works. It should not work. That's why Jupyter for these things is better. So test2.py, yes, so time in it is not invalid. So let's now fix it. So here the first thing is that we did is import time, and then we'll write start time is equal st is equal, and then we'll say time dot time. So this will tell the time right now, time dot time. Okay, and after that, then we should perform the operation and then say the end time. So now this is the operation that we're doing. Let's call this, we're just having some, and we're just raising it power to the 2, and then we'll say end time en, and we'll again say time dot time. Okay, and then we'll say print start end time minus start time. st. Okay, but I think there will be very less difference, so hopefully you should be able to make it. Okay, now if I run this, so this is that 4.64916 e to the power minus 0.0. This is in seconds. Okay, this time is in seconds. So now if I do it with NumPy, so by NumPy I mean I should just there is a function, let's call that's np dot range. So here we call it a range, and the similar thing is we'll have the 1000 elements, and I should import NumPy also as np. Okay, and then I'll just square the number. So how to square it is basically a square like this. So we have the here L. This is how to square. And now if I just, hopefully, yes, you can see the time difference. Okay, so this is almost half. This is not just half. I think if you keep on operations, but here I just showed you basic example. So it usually is like 4, 5, 10 times faster than this. So here we did it by on the list, and you saw this is the time. So 4.6 into 10 to the power minus 5 in second. So here you can see 2.57. Okay, and this you can see the difference in clear. The operations done were pretty much similar, but if you see the time we saved is almost we saved the half time. Okay, if it initially took some 4.5 seconds, now it took 2.5 seconds. Okay, not just seconds, it is into 10 to the power minus 5. Okay, that's closer to microseconds. Okay, 0.4 microseconds or something. So I hope I was able to show you this, how fast basically NumPy is than the predefined data types like list, tuples, and now you are at least convinced that you should use this for numerical computation. Okay, and you will see that most of the people who do this deep learning, machine learning, they'll use this for the numerical computation. I think we have a pending question. Yes, any questions they can ask. So now you saw that how fast this NumPy is, and there is a lot of performance and speed gains that you get. Okay, I'll just write them for the sake of completion. Why NumPy? Okay, why should you use NumPy? For the sake of completion, so that if you have to sometimes know it, why should we use? The first thing is efficient operations. Efficient operations that we saw. So NumPy operations are faster due to the implementation in C. Okay, and the optimized algorithm. So it enables them to handle very large data sets, and there is something known as called as vectorization that will look I think in a while. So this is the first, the efficient. If you perform these operations on NumPy and D arrays, so it will be efficient. Okay, and the reason is because the code is written in C, and there is something called as vectorization, and the thing is broadcasting. We'll see all of these things, but the first primary reason is the code is written in C, and now the second thing is it's also memory efficient. Memory efficient. Okay, so it stores it compactly. So NumPy arrays consume less storage compared to the Python lists. Okay, and it makes the memory efficient because it reduces the overhead of allocating different memory, because as I said, there is this need that you should have the element homogeneous, so that it allocates memory upfront, and it has the compact representation. If you people want to see how it represents, you can go on the official documentation. There you will see things written about it, and you can easily understand them. Why is it memory efficient? But here what you can see is, because I said it takes homogeneous elements and it stores them into the run one after the other. Okay, and it saves a lot of overhead that lists has. Okay, and then we have these optimized functionalities. Optimizations. I'll write optimized functionalities. Okay, so NumPy's core basically all the operations that are mathematical operations. It was taken into consideration that we should write and we don't have to make it generic. As the list was made generic, you can have this element, you can do this on lists. But this was particularly made for scientific computation. So it gave us a room that we can optimize these functionalities. So people who wrote the NumPy code and they tried to optimize all these functionalities that we had. And then we had this interoperability. I should rather write in the same color. Interoperability. So all these, most of these things are written in the Python official documentation. Interoperability and integration. So what you can do is you can integrate this code easily. By interoperable, I mean is you can just use this code somewhere else also and integrate with some other libraries. Okay. So let's suppose you can use it with SciPy, you can use it with Pandas, you can use it with Matplotlib that we're going to see. You can use it with TensorFlow. You can use all this code because it's interoperable and it is the integration becomes also easy. And now these are the core features why you basically should use it. And then other reasons that we have is it makes analysis very easy. It makes data analysis easy. If you are analyzing data, it makes data analysis very easy because it can read the data and have the compact representation and then perform these operations very efficiently. And then one more important aspect is that it is open source. Oops. So it is open source. Just let me clear this. So it is open source. And a lot of community support. Okay, so data analysis becomes easy because of these things, and after that it has made open source. As I showed you that you can also contribute yourself. And the third thing is that it has a lot of community support. If you are facing an error, you can just write the error in the Google and then search it. You can get websites like Stack Overflow. You can go to the websites. You can go to the official documentation numpy.org and you will find the solution there. So these are the things that makes it very useful, and that's why you should use NumPy. Okay, and now we'll go into technical discussions, and done with this, I just wanted to cover it. Okay, now why is it fast? Okay, now the question is why is it fast? I said there are two problems. Why is it fast? Just some background covering. So there are two main reasons why is it fast. The first thing is called as vectorization. Okay, so what is this vectorization? So it basically is we don't use explicit loops. So here you don't use loops. Okay, you don't use explicitly defined loops. So what you have done basically is you have pre-compiled C code. Okay, we have pre-compiled C code. So as I just showed an example, if you just want to multiply two NumPy arrays element by element, you can just say multiply. Okay, and if you saw in the list, we have to run a loop. So what they have done is internally they have pre-compiled the whole thing. Okay, let's suppose this is a list and this is one list. If you have to perform, you access this element, then multiply them together. Okay, multiply this and sort together. But if you see in vectorization, what they do is they have vectorized this. So if it is a NumPy array, so it will occupy space and it will occupy. This is, let's suppose, NumPy, and this was list. This was list 1, list 2. This was our NumPy 1 and NumPy 2. So here you won't use explicitly these loops. There will be a pre-compiled C code which will take these elements all together and multiply them one by one in the one go. Okay, and that is the beauty of this having these optimized pre-compiled this C-written code. Okay, and this is one of the reasons. So this is called as vectorization. Okay, so vectorization basically means absence of explicit for loops. It is not using explicit for loops to just access the element. If you see this operation like quite naturally. So first thing is you have to access this element, then you have to access this element, then you have to multiply them. Then for one operation you have two accesses, then multiply and then write them in somewhere. And similar thing is done for all elements. So here what I said is, so there is a pre-compiled code. These are stored somewhere. It just needs the address and the size. This is the size of the list. This is this is the size of NumPy array, this is the size of NumPy array 2, and this is of the type, and then you can just multiply and you can perform the operation, not just the multiply, and you can do the other operations. And then it saves that Pythonic nature. Okay, by Pythonic nature I mean the code writing or code readability is the similar. Okay, and it is the ease of programming is not taken away. It shows you that interface, but internally it performs these things very fast. And then there is one more thing that's called as broadcasting. The first thing we said is vectorization, and it is the absence of these explicit loops. And then the second property, why is it fast, is because of the broadcasting. So broadcasting basically means, so element wise these operations. So in these NumPy, not just arithmetic operations, but these logical operators maybe which are done on element wise. So they basically they broadcast to each other. So we'll see in detail what broadcasting is. So right now what you can see is, so for each of these they basically let's suppose we have this 1 and 2, and then we have a list 1, 2, and 3. I'll just give you a simple example: 1, 2, 3, 4, 5, 6, something like this. So now you can see the mismatch over here, but they'll broadcast its shape to each other. Okay, so that these things are, let's suppose we can have a list like this where there'll be these numbers will be dummy numbers or something, so that these operations where we need these loops, these explicit loops are not used. So we'll broadcast basically size of this. So we'll say size of this is this. So make it somehow so that you'll have these multiplication sort of this. And otherwise there are a lot of types of broadcasting, not just one type of broadcasting. So you can just repeat this 1, 2, 1, 2, something like this. Okay, we'll see in detail what broadcasting is, but for the sake of time being, you just keep that there are two things which make this NumPy fast. The first thing that there is, this is called as vectorization, and the second thing is, this is called as broadcasting. Okay, these are two things which make this NumPy fast. Now we'll understand this ND array. As I said, this is the core in NumPy, so we'll now try to understand what this ND array is and how to create this, what are the different things that we can do with it. So now this is if you see what array is just a run of numbers, and I don't need to motivate you why do we need a run of numbers, because we have been looking at left, right, center. So these numbers are the things that computers store, these numbers are things that computers manipulate, and everything basically inside a computer is just a number. Okay, talk about image, talk about pictures, talk about videos, talk about audio, talk about anything that is there. The data basically is numbers. Okay, and that is what this store. This is basically consider this as a container. Okay, which has these numbers. Okay, so this is the fundamental data structure. I can write this core or fundamental core / fundamental data structure. Fundamental data structure in Python, in NumPy. In NumPy. So again, I'm reminding you one thing, I won't probably just teach you NumPy. So what I'll do is I'll teach you the concepts that NumPy has used, and same concepts will get repeated in PyTorch, let's suppose. So we'll see slicing, we'll see indexing, and we'll see a lot of concepts that we'll see in NumPy, and it will get repeated in Python. So concept will remain similar, but the implementation will be changed, and then there are a lot of stuff that people can do in different ways, but the core concept remains similar. Here what you see is this core fundamental data structure in this NumPy is ND array. Okay, what are the key? What is this basically? It'll be a run of numbers. Okay, we'll store numbers, store not just numbers, maybe store whatever data type we have, because it supports a lot of data types. Okay, and underneath this everything is a number. So it will store this data, it will store the data types in this ND array. Okay, now the first thing is it's indexed. You can index it. Indexed. Okay, so what is the meaning of indexed? Let's suppose if I just make a representation, so I can make it like this, as we have list. So this is 1, 2, 3, 4, 5. Okay, so you can index it. You can index it like this: 0, 1, 2, 3, 4. And here we have negative indexing also: -1, -2, -3, -4, -5. Okay, and this we'll call as a 1D array, or 1D array of NumPy. Okay, so this is ND, basically we'll just represent it 1D array in NumPy. Okay, and this is usually called as x is 0. X is 0. So as I said, by default, when we were learning about linear algebra, I said when I talk about vector, so vector you should consider as a column vector. Okay, this vector basically is 1, 2, 3, 4, 5. If I write in mathematics, so this is the vector. Okay, this is that column vector. That's a 1D array. Now if I have this 2D array, so 2D NumPy ND array, basically 2D array. So that is array within the arrays. So it can be thought in two ways. So if you see it like this, so it can be thought in this. You have an array like this. So each element of this array also is an array. Okay, something like this. So this is one. This is how you can think of this 2D array. Or you have another representation, another pictorial representation. You can just think it like matrix. Okay, so this again is a 2D array. So here this also is a 2D array, and this also is 2D array. Okay, representation of the 2D arrays. So now what we call, you will call this x is 0, and this is x is 1. Okay, so here you see the first is how many basically elements you have. Within that element you have this. So if you see this, I call x is 0 initially. Don't get confused that I wrote it horizontally. So I said by default the vector is like this. By default, when you think about an array, So you should think about a vector. You should think about a column vector. So that's why this is x is 0. I should, because this is like this actually. So when I wrote it in 2D, so 2D, this is x is 0, this is x is 1. So what about 3D? So 3D can be also thought in this tree structure. Now each of this again has more nodes. Okay. So you can think it like, let's suppose we have an array, or let's suppose 3 elements. So each element is again an array of 2 elements. Say 2 elements. Okay, and now each of this again is an array, let's suppose of 3 elements again. And for this also. Now how we can think also these 3D arrays is, initially you said, rather I said, not you. So we had this 1D array like this. Okay, when we stacked these two things together, so we came up with 2D arrays. We stacked them together. So this was 1D array, this was 1D, this was 1D, we stacked them together. So this became, so stacking of 1D gave rise to 2D. Now what if I stack these things again? Now we have this, so this is our building block. So this thing is our building block. Okay, now what I can do is, I can stack these things again. So I can stack it like this. So if I have like this, so you see now I have 2D, I have slices of these arrays. So if I just make it, I have slices of these arrays. This. Okay, it looks like a cube. If you see it like this, it looks like the cube, and each of this slice is a 2D array. So this we'll call as axis 0, and this is axis 1, and this over here is axis 2. Everybody clear? Now you can also imagine 4D arrays. How can we imagine 4D arrays? Now we'll stack these things together. Okay, how can we stack? So let's suppose we have this 3D. Okay, and we have another 3D over here. Okay, and now if I call this, I can call this a 4D array. Is it clear? So now I'll show you in numbers. So if you see how I showed you, this representation should be clear, because this will be used throughout everywhere in programming. So if you see, if you are talking about 1D, 2D, 3D, ND arrays, so this is the picture that should pop up into your head. Okay, everywhere, not just for the NumPy. I'm saying for every array. So whenever somebody says a matrix, a tensor, or whatever, it just terminologies will be different, but more or less the concept is similar. So if you have a number, that's one number. This is a scalar. Okay, we have a scalar. This is scalar. The scalar is just one number. Now coming to the vector. So what will happen is we'll be working with this 1, 2, 3, something like this is a vector. Now here we saw that we put these scalars together, and this is a scalar, this is a scalar, this is a scalar. So this is a vector now. Okay, now if we put these vectors together, we come up with these matrices, or we come up with ND matrices. So by default, this is actually a column. So what I do is, if I have to make it in rows, I can make it like this. So this is a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a 2D array, or 2D matrix. So this is scalar. This is 0D. So we call it 0D because it has no dimension. So here this is 1D. Okay, here this is 2D. Now if I have 3D, now I'll put these things together. Okay, 3D basically is like this. So you will have this, and you'll put these things together. Okay, so what is 4D then? So 4D is take these 3Ds. Okay, I should make it on separate page. So this is my 3D. Okay, if I stack them like this, and another 3D. Okay, putting them together, this is 4D. I can also create a 5D like this. So this is 4D. I can also create 5D, 6D, 7D. So this is the image that you should have in your head. And when you club these things together, now when you put these things together, and that's why the role of brackets will come. So now I'll see you how is the role of these braces, square braces. So if I have to just define a scalar, I'll say a is equal to, this is a scalar. Now if I have to make a vector, okay, so I'll say a is equal to 1, 2, and 3. Okay, because now each of this is a scalar. So if you see, each of this number is a scalar. This number over here is a scalar. So now what if I have to make, this is 0D and this is 1D. Now what if I have to make 2D? So what I said is, now you have to put these things together. So what I can do is, so this is, I'll write A0, A1. So this is now A2. So how I can write A2? So A2 is like this. You have a brace, and within that each element also is each element is 1D vector. Each element is a vector. So I can write 1, 2, and 3. Okay, and then comma, and second element is also there, 8, 9, 10, let's suppose. Okay, and then we'll put these braces. So each of this over here is 1D. Each of this is a 1D array. So in here, if you see, this is a scalar. Scalar is the basic building block. Okay, then from scalars we created what's called as 1D array, 1D vector, 1D matrix, whatever you call it. Okay, so then each of the element basically was of 0 dimension. Now when you move to this 2D, so when you move to this 2D, each of this element now, each of this element is 1D. Okay, again if I call A3 now, so what will be A3? So this will be first bracket and then second, so we'll have this 1 comma 2 comma 3. Okay, and then we'll have one more because it will be a matrix now. So internal element will be matrix 4 5 6. Okay, so if you see this, this is one element of this. Okay, so I should rather see from here to here. So this is first element. This I'll make a little bit bigger, this bracket. So this is the first element, let's call it 0th element, and then if I write the first element, so first element will be written like this. So this is minus 1 2 3 6 8 6, something like this. Okay, and this is the first element, and I'll write this bigger bracket. Okay, understand this. I think till here this was easy to understand, but here the things are starting to get a little bit juggled. Let's see. So if you see, if I told you I have a 2D array, 2D array means each element in it will be 1D. Okay, you understand what 1D is. So this is 2D array. So in here this is the 1D, and second element is also 1D. Now when I came to 3D, so I told you that you should think it like each element will be 2D. So if you see, this is the element, and now if you see, this is 2D. This is like this. Okay, 1 2 3 each, and then within that 2D each thing is 1D, and within 1D each thing is a scalar. Okay, so this thing if you see is the first, is the 0th element, and this thing over here is the first element, and this is how I have defined this A3. Now if I have to create 4-dimensional array A4, so now each element will be a 3D structure. Each element will be 3D. So by 3D I mean, so you should have this, and you should basically have matrices. You should keep this together. Now whole of this will be the first or 0th element or the second element if I index it. So is it clear? Can you now generalize it to ND? So for ND, if you take one element, that element will be of dimension n minus 1. So for how many people can I assume that this is clear? For how many people is this concept clear, that which I taught about arrays? So I told again it's a generic concept, nothing to do with NumPy. It has to do with everything that you'll encounter in probably TensorFlow, PyTorch, wherever you see these wherever you see these arrays. Is it clear? If you are given an ND array, so basically that each of the element will be a n minus 1D array. Okay, let's suppose if we have 2D array, so each element, the first element, second element, third element, these will be 1D elements, also which we'll call basically let's suppose these vectors. If within 1D, each element will be a scalar. Okay, that's how, if you see, this whole recurrence is going on. So you have ND, n minus 1D, and then we go on, and that's why sometimes people think it as like tree structures. So root basically are scalars. So if this concept is clear, you have done yourself a great job. Why? Because it will be really easy to understand slicing everything now. So here this root, basically this each element will be a scalar, and then you can think it like this. And the best way to think in terms of this is in terms of these diagrams. Okay, you put these scalars together to come up with vectors. You put these vectors together to come up with a matrix, and that matrix together you come up with these tensors, or we call them ND arrays. I think we have a question here. Let me just take that. The question is, term dimension we learn in algebra is different, right? Yes. We will come to that because these terms are overloaded. Okay. So usually that thing is called as rank. Okay. So now we have this ND array. You understood the structure. Okay. Before going to the coding part, you should have these basics really, really solid foundations. Now what we'll do is we'll see what are the properties these things. They have key features. The first thing is I said it's an indexed grid sort of thing. You saw that how the grid looks. Okay. I said the first thing is it is indexed. And from the index we had this discussion that we saw how to basically visualize these structures. And the second thing is they have a rank associated with it. So rank basically means dimensions. So by dimensions I mean is it a 2D, is it a 3D, is it a 1D matrix, okay, something like that. So rank, it basically signifies dimensions. I'll now call them dimensions. But in the official documentation they named it as rank. They're just names. Okay, names you can name them anything, but I hope that you got what dimensions means. So if I have 1 2 3, so here if you see this is just one row. The rank of this is because this is 1D, so I can write this has rank 1. Okay, this is 1D. If I wrote something like this 1 2 3 4 5 6, good writing, this should be actually written like this. Okay, so this is now having rank 2D. It has dimension 2 dimensions. It has this axis 0 and axis 1. So this only had axis 0. So this has axis 0. Here axis 0 is this. because now that you'll appreciate that fact why I said whenever I talk about this bunch of numbers array, you call that a column vector. Okay, whenever I talk about a vector, you understand that column vector. So basically this is a column vector. So now this is axis 0 and this is axis 1. Okay, and this is rank. So what is off-shell document inheritance rank? Rank basically is dimension. It signifies the number of dimensions. So here this is, if I tell you about dimensions, let's suppose we have things like line, it's 1D. I think we had a discussion like this also. So if we talk about these planes are 2D because they have a length and a breadth. So here they have only length. Now if I talk about 3D objects, let's say 3D like this pen. This pen has length and breadth and height also. This has three things. Okay, so length, breadth, and height are 3D. The number of dimensions, number of numbers that you use to represent here. So here if you see, so here you have this axis 0 and axis 1, and here you have axis 0 only. So if you have a 3D matrix, there you have axis 0, axis 1 and axis 2, and you can keep on increasing this for the n dimensional things. Okay, I think this index is clear and this rank is clear. And then we have a shape. This is the third property of this. We have the shape. So what is shape? Shape basically is a tuple. If you see, it will return it's a tuple, or people pronounce it tuple. So this tuple is there. So if I wrote something like this, so I have 1, 2, 3, and then I have 4, 5, 6. Okay, this is how I define my ND array. So now if you see this, so this is actually a 2D array. So I am sure that there will be two dimensions. Okay, there will be two axes, axis 0 and axis 1. Now I need to see the number of elements. So if you see this, so there are two rows. Okay, so axis 0, so this is axis 0. Axis 0 has 1 and 2 rows, so I can write 2 comma, and each of the columns axis 1, if you see this axis 1 has length 3, so I can write 2 comma 3. So this 2 comma 3 is shape. 2 comma 3 is the shape. So if I make a matrix like this, if I have 3D matrix like this, okay, so first axis 0, axis 1 and axis 2. So now the number of elements in that, so number of rows and the number of columns and the number of slices. Okay, so this is rows comma columns comma slices. So this is the shape. So let's suppose here if number of rows is 4, 1, 2, 3 and 4, and let's consider 5, 1, 2, 3, 4 and 5. So here if you see, this is 5, and let's consider this as 3. So 4 comma 5 comma 3 is the shape. This is the shape of this ND tensor. The first thing is we saw that is an indexed grid, and the second thing that we saw, there is a rank which is called a dimension. Then we saw shape. So these are the three important things that we saw. How many of you understood these three things? Now if I just summarize what have we seen so far, we've seen why to use NumPy, why is it efficient, and then we saw okay, what is it providing differently, and then we had a discussion on how to think about these ND arrays, or how to think about, usually people may call them tensors, matrices, how to think about these, and in NumPy they are called as ND array. Okay, how to think about that. Now we'll see ways to create these arrays, okay, in NumPy. Ways to create the ND arrays. There are 6 ways. Why am I so confident about only 6 ways? Because this is what is written in the official documentation. So there are 6 ways. Okay, and we'll take everything one by one. The first thing is, the first way is conversion from other data types. So conversion from other data types. Because you might have a list, and you might have, let's suppose, a tuple, you might have a dictionary or something, and you can just create these from these other data types. So let's see that first. Okay, let's go to the coding window and show you that. That's the first way. I think I've showed you for the lists. So this is, let's create new test3.py. It's really difficult to type and write. This is code test3.py. Okay, this is and now if you have a list, and you can just create that. Let's suppose I'll say I create a list. Let's have a tuple now. Let's call it tup, and we have this 1 comma 2 comma 3, something like this. So the similar function is, we'll have to import NumPy first. Import NumPy as np, and then if you have this tuple, you can just say array is equal to np.array. That's the function, np.array, and then you can see this tup. And if you just print the type. So print type of this tuple, and at the same time you can print type of this array. Now after this conversion. Okay, now let's save it, go here. If I just write Python test.3, so you can see that initially it was a tuple, and then we had this class NumPy ND type, ND array basically. So this is the first way. You can just have predefined data structures, and from that you can create these NumPy arrays. And that's the first way. And the second way I'll say is, just going back, oops. So this is the first way, and we'll also have more discussion on the first way. Now we'll see the second way. So second way basically is you have intrinsic functions. So this is the second way. The second way is you have this intrinsic functions. Intrinsic functions. Okay, so you have these intrinsic array creation functions. Let's suppose you want to create all zeros. You want to create a function. You want to create a run of ones. You want to create an identity matrix. So for that you have functions. Okay, let's go back to the VS Code and see that. So let's say you want to create all zeros. So what you can do is, let me comment this code, and you can see. Let's suppose I'll write import NumPy as NP. So now if I want to create something, I can say, let's suppose array of ones. If I have to create a run of ones, I can write np dot ones. This is literally a function, np dot ones, and then give the size of this. Let's suppose I want to create let's suppose 2, and you have to write the documentation. You have to see the documentation how to create that. You can just go the print array ones, and now if I just run this, oops, array ones, I think ones is the function. You'll have to see, oh, ones like not ones. So now we'll have to see if it runs. Yes, so you can see that I created a run of ones. If you see this array of one, it create one. Array zeros is also a function, array of zeros. Okay, and here internally it takes size. So if you see the signature of this function, so say it takes the shape. Okay, and here I have given I just wanted to create 1D. So if I now create, you can see 0 0. If I have to create 2 3 a matrix, I can just give the shape. Oops, but I think I should give it as a tuple as a size. So what I can do is, that's why you should write the signature. So you can see this. So I just created 2D array which is of dimension 2 3, and then this is 2 rows, 3 columns, and all these zeros, and like this ones. Oops. So again 2 3. So this is 1 1 1 1 1 1. So this is one of the ways, and then you can also create identity. I suppose there is this EYE identity element. Let's cause 2 cross 2. I hope this is identity. Usually, not usually, identity is a square matrix. So if I just create this, you can see this 1 0 1 0 1. So this is identity matrix of size 2. So if I have to create identity matrix of size 6, and if I want to also check the type, so what I can do is print type of this array ones. So it should give me this NumPy ND array. Okay, so these are interesting. There are a lot of methods also. Okay, there are other methods. I just showed you maybe ones, how to create zeros, ones, and how to create this identity matrix. And there are humongous number of methods that are defined in NumPy. You can just check the official documentation and this documentation. And if you see this I, so here it is defining n is int mk, and everything signature is there. Okay, and you can read about the parameters. Okay, and this is the VS Code's functionality. You can just go on this. If I click on I, it shows the function signature. So m here is number of rows, and m here is a number of columns. K is optional index of diagonal element. Okay, and D type is what is the data type that you want to create. Order, whether the output should be stored in row major or column major order. We'll also see that what row major or column major order is. We'll also have a discussion very briefly. And then you also have array functions, and then it returns an ND array. So this is the documentation, and it also gives the examples. Okay, and I showed you this. So this is how you create. The first method was to create it from data structures, data types which we already have, and second thing was you have intrinsic methods to do this. Okay, and these are the intrinsic methods where you can see it. And now what I can do is I'll show you in general. So in general we'll also have some discussion of these D types. So if you see this array, so I want to create an array. So I write np dot array. Then I'll create an array 1 comma 2 comma 3, 1 comma 2 comma 3. So what we can do is we can check the d type. So by default, what is the d type? So I can say print and array dot d type. There is this d type which can be defined on this. Okay, I want to check what is the d type of these elements. Okay, so if I now run this, so you see this d type by default is integer 64. Okay, so int 64 is the default d type. Okay, I hope it's clear. So here they have given us, if you see the signature of this function, if I just hover over it, you can see define array. Okay, this is definition, and it takes an object. D type is d type none by default, and it can also take values, and then copy more, and there are all these, and here you have written, you have the whole of this documentation written. Okay, copy is true, then the object is copied, otherwise a copy will be made. Okay, d type, but we'll just have a discussion on d type. So what I can do is I can say d type. So I can say d type, and I can define this d type on my own. Here by default it is int 64 or int 64. Okay, all in the small caps, int 64. So this is default also. Now I am overwriting this. It should not give me an error. It does give me an error, so I don't know what to write. D type. Let's go to array again.
np dot
np dot d type, maybe. Is it? Yes. So np dot. Yes, it's int 64. So what I can do is, so here again you can just hover over the, if you somehow don't know the syntax, you can just hover over these things, or maybe just once Google search away. Okay, and if it is throwing some errors. So here it is not given. NumPy will try to use by default int 64. So that's written over here. D type can be represent the values by applying a promotion rules when necessary. Okay, and we'll also see the promotion rules. So let's suppose now I will write I'll say 126 comma 127 comma 128. Okay, I'll just print this array. So what should be the answer of this? Anyone? Give me the answers. If I run this, what should be the answer? Arshan, Fahad. So if I just print it, I just create an array 126, 127, 128, and I said d type is equal to this, print array. So what should be the print on the screen? Are you guys here?
Yes, we are here.
So what should be the answer? Hey, it's
It
obvious.
should be the array elements.
Yes, array element 126, 127, 128. Okay. And if I just type, and it should be this. So let's suppose I'll write, let's suppose int 8, if that is there. Yes, int 8 is there. It is in the signature. So what do you assume? What should be printed? I'll wait for a couple of seconds. Yes, Fahad.
126, 127, and 0.
Okay, let's see.
Not 0, but something in minus.
Something
Yes,
else,
minus
right?
120.
Because we studied
Yes,
this.
yes.
If you remember Python, so we studied this, because that I just wanted to just remind you that here int 8 basically means it is an integer, but it is only having 8 bits. Okay,
Yes.
so
2 raised to 8.
okay, by 8 bits I mean, so you'll have something like this: 1 2 3 4 5 6 7 and 8 bits. And now you know that these numbers are saved in 2's complement. So first bit will be most significant bit. It will be saved, it will be for sign, if it is signed representation. If it is 2's complement, then we'll use all the bits. So the number that will be represented is 2 to the power 7 minus 1. So that is, this will be the range. The range of numbers is 2 to the power 7 minus 1, negative of 2 to the power 7 minus 1 plus. So this is 127 minus 2, 127 plus. This is the range. Okay, so once I did this, once I said 128, it got out of the range. Okay, that's what overflow happened. Okay, we call it overflow.
Yes.
So overflow happened, it showed answer as minus 128, because it does what's called as wrapping around. Okay, so I hope this was clear. So you should be very careful when you choose data types. So sometimes you should also think to not give unnecessary space. Let's suppose if you use int 32 and it does your job, it's really nice because you are saving a lot of step. Let's suppose you have some millions of operations, you have the millions of numbers stored. So if you are just using the half precision, okay, and usually it is 64, but if you can use 32, you basically will be storing, you'll just use the half space. You'll use the half number of half the memory allocation that we usually use by 64. So you should also use this feature very carefully, so that if you have a certain specification or you have a certain need, that need is met by showing this. So this is one of the data types that I wanted to show you. So coming back to the code, I also wanted to show you this, the question that I think earlier was asked. So now if I just remove this, if I just check the dtype dot dtype, and now if I run this, so you can see it is int64. What if I write something over here? Let's suppose I'll say 127.0. I made it a float on purpose. So now if I run this, you can see that everything was a float 64 now. So I said this is homogeneous. So when the one number was defined as float, all the numbers were made floats. Okay, because I told you that one property that these ND arrays have, these NumPy arrays have, they're homogeneous. That is, they store each of the element in the same data type. So here you see this 126, and then I wrote 127.0. It made a float, and the whole thing is made the float now. Okay, what about the string? So if I just wrote a string over here, hi, it does support it, but what will happen is it will change the all data types. So if I just click it, so it is showing something as U32. This is a data type, the custom data type that was created, where everything was stored like this. Is it clear? Okay, you can create these things, okay, but it'll change them into U32. Okay, if you have this mix of these things. So this 126 again is this less than this is a data type, and you can learn about it more. And if you want to see how what is the custom things, what are the properties that they have. But one thing that you have to learn is that this ND array of NumPy, it stores homogeneous elements. So if you have one element that does not fit in description, so it will try to see that precedence order. Okay, I'll convert it into U32. If it's a float, okay, everything is a number, let's have everything as float. If everything is an integer, let's have them as an integer. Why? And that's why that's how it makes the operations faster. Okay, that's how it makes operations faster. I hope this was also clear. Now we were looking at the methods. The first method we saw is you can have these default data types like tuples, lists, and even dictionaries also. You can also have them and just call this np.array, and you can create. And second thing is we had some intrinsic methods. So intrinsic methods, by intrinsic I meant let's suppose these EYE if you want to create an identity, if you want to create zeros, run of 0 if you want to create ones. Okay, you can have that. We also saw that. And the third thing is the third way of creating. I just want to remove this VS Code. The third way is basically having these replications. Okay, we call it replicate, and there are different methods. You can replicate, you can join, you can mutate. Okay, and there are existing arrays. So if you have an existing array, so I'll write replicate, join, mutate existing arrays. This is also a type of creation. If you want to create something, so maybe there is something existing and you want to do something on it, but you are creating a new thing out of that. So you can use these sort of methods. So what you can do is you can have a previous array, and you can have functions like np tile, np concatenate. You can have these other flip, transpose. You are doing something on what is existing there. There is an existing thing. So you are doing something on that and creating new arrays. On the new arrays basically are NumPy arrays, but this is the third method. Okay, and the methods are like, let's suppose np concatenate. So what it does is it concatenates two arrays. If you have two arrays, it will make a third array by which it will concatenate. Let's see that in action. I hope this should not be very different. So if I have, let's suppose, array 1, comment out this code. So array 1, this is equal to np.array, and then I'm just creating 1, 2. This is one array. Oops.
We are not seeing this.
No problem. I'll just. Yes, I hope now it's visible. So I'm just creating one array, and this is array 2. I'm saying np.array and creating 4, 5. And now I can just array 3 is to be created. Now what I'll do is I'll use existing array. So this is the third method while I'm using existing array. There is this array 1 and array 2. What I can do is I can say np.concatenate. Okay, and then I can see the signature of this. Okay, I will you can see that you have to give a sequence of arrays. I'll give array 1 and array 2. Array 1 comma array 2. Array 2. Oops, array 2. So now I can basically print this array 3. So here if you see this, so now I'll again run. Oops. It is showing some error. So type only integer scale arrays can be converted to scalar indexes. I think I have to do something with axes, but I hope you got the concept. This is the error, and we have to just debug it and how to basically take it in the right, and axis is optional, but I suppose it should print it. I don't know why is it not creating, but it should create it. So array function internal line 180 concurrent only integer scale arrays can be converted to scalar index. There is some error, yeah, and you can look at this, but this is the valid function. So this is the third method. Okay, I don't want to spend much time on debugging the code. Okay, and there are other functions like this. So there are other functions where you can replicate, transpose. Okay, and all of these things are there. So this is 3 methods so far. But do test them out. I am not on purpose debugging them because it will unnecessarily take much time, and our time is more important to learn about concepts rather than debug the code. Okay, the first method was, just to reiterate, the first method was conversion from other data types, and then the other thing was intrinsic functions, and the third was operations on existing arrays, operations on existing ND arrays. Okay, now the fourth thing that we will see is that's reading arrays from the disk. Okay, what you can do is reading arrays from the disk. This way also you can create arrays, because let's suppose you have stored some data onto the disk. So what you can do is you can read them. You have let's suppose a function called np from file, np dot from file, np dot from file, and you can give the path of the file over here, and you can read it as a NumPy array. Okay, and then this will again create an array. Okay, this is one other method. So these are 4 methods, and then we have create arrays from raw bytes. So if you have raw bytes in the memory, you can create arrays from them. Create ND arrays from raw bytes. Okay, and you can just let's suppose use np from string. If you have, let's suppose you have these raw bytes in the home string, you can use function like np from string, np from a buffer, and these sort of things. And last is you have specialized library functions. So use of specialized library functions, specialized library functions. So these are all the things mentioned in documentation. I just wanted to show you them. Let's suppose if you want to create distribution. Why is it called special library functions? Let's suppose you want to create a normal distribution, a random number. You can write np.rand. So this will create a random number. You can, let's suppose, say np.random.normal. I myself even don't remember all the functionalities, but the thing is, if you need something, you can just go over there. Okay, so this over here will create a normal distribution, let's suppose. Okay, and if you want to create some other distribution also. Okay, and this should be np.random.rand. This will generate a random number. Okay, this will generate a number which comes from a normal distribution. Okay, by normal I mean this mean should be 0, and I think standard deviation should be 1. Normal distribution is written like this, and we'll see what these distributions are. But these are some special libraries where we can you can, if you see this NumPy, and then there is one more thing, dot random. So you have NumPy, inside that you have this random functionality. This basically in itself is a library, or you can call it a module maybe. So here in that rand you have this random number generator where you will have this random number. Okay, now we saw 6 methods. Okay, 6 methods, and I hope that once you will see this lecture, and you will try to find maybe not all the functions, maybe some functionalities, and have some of the experience with all of this. You will try to convert from other data types. You will try to use intrinsic functions. You will try to operate on existing arrays. You will try to read from the disk and create these from the raw bytes and use this specialized library. So these are the 6 methods by which you can create this NumPy array. Is it clear? I hope this is clear. There was nothing new, because this was the just functionality of the NumPy, and how in NumPy how you can create these ND arrays. Now under a generalized concept. Okay, now this was related to NumPy. Coming back to the generic concept. Now there are attributes to these attributes to these ND arrays. This is not only applicable to these ND arrays. It's applicable to matrices. Okay, because we saw something. We saw shape. I think we saw some of these things somewhere. I think over here. We saw shape. We saw these 3 things. We saw shape, and then we saw rank. We saw indexing, rank, and shape. Okay, we'll see some additional features that there are with these ND arrays. Okay, the first thing is dimension. You can just say ND ndim. Okay, so it indicates the number of axes of the dimension array. Okay, if you just write nd.dim, what I can say is it will indicate the number of axes. Okay, axis number, which I said axis 0, axis 1, axis 2, and then we have shape. I'll just write shape. Shape, it will be a tuple, and it will be array. It will basically a tuple and showing you, like, say, let's suppose 2 comma 3, and we also saw that. And then there is size. These are all attributes. You can just call them on the array. So this size basically represents the total number of elements. So this is total number of, this is new, total number of elements. Total number of elements. Okay, I think this deserves to be shown. Maybe we'll see them together after in the code. So size, basically, if you have like this 1, 2, 3, and this is a list. This is basically ND array. If you just call dot size on it, it'll give you the size. Or if you have something like this 2, 4, 5, and this is a 2D array, it'll show 6 because the size is 6. 6 basically means total number of elements that there are. And then there is D type that we also saw. We saw this shape, we saw size, and we saw this D type. And then there is item size. Item size. Item size is it denotes the size in bytes. Okay, size in bytes of each element. So if you want to see what is the size of each element in this ND array, so you can just call item size. Okay, and then there is dot data. This is one more attribute. So okay, it contains basically buffer holding the actual element of that array. Okay, it's a buffer. So let's see the usage maybe, and I'll just copy a lines of code because I have created a notebook for this. So I'll just write code test4.py. Okay, and then a new file should get created. So here, if you see this, oh, I have not talked about reshape though. Anyways, so we'll also see this reshape function. So what it does is, so this A, if you see this line of code, so I will just open the VS Code for you. So here, if you see this, the first line is a np.range. You know what this does? So this is a range. It will create 15 numbers, 0 till 14. Okay, and then I'm saying reshape. Reshape basically means reshape it because it will be just one axis 0. I'm saying reshape it 3, 5. If I just print a, so this print a should print the whole of this. It will print 3 rows and 5 columns in which the numbers will be from 0 to 15. If I just comment out this, and I'll keep on printing it. So if you see, this is code. I should write Python. This is A, because A range, it creates those 15 elements starting from 0, and then the reshape, it reshapes it. And then I'm printing this A. Now if I want to print the shape, now you know the shape. Shape is 3, 5 because that's how I reshaped it. So if I now want to print shape, so this is the array and this is the shape. Now I'll keep on commenting these previous things also. Now if I have this ndem, because this is a 2-dimensional thing, because it has axis 0 and axis 1, the number of axes, the number of dimensions. So if I just run it, it is 2-dimensional thing. Okay. Now if I want to see this dtype.name, okay, I'm saying there is this dot name. So I'll say a.dtype.name. So if it should output in 64, because by default this is what the dtype is. Okay, and then I can create item size. What is the size of each of this? Now it is in 64 bits. So if you convert them into bytes, so 64 by 8, that is 8 bytes. So this item size should show 8 bytes. So if I just comment this, and you can see this, this is of 8. 8 means 8 bytes. So if I just print the size, you know how many elements are there? There are 15 elements. It should output 15. Okay, this is the 15 output. And then if I say type of A, this should give me the D type. This should basically create this class NumPy ND array. Okay, have we left something? Okay, we have also seen data, and yes, I think we have covered these things. So these are the attributes that are there with probably not just with these NumPy arrays. Maybe with the tensors you will deal with PyTorch. Maybe you will also deal with different matrices where you will create, and you will see these attributes there. Okay, these attributes will be, you can create shape, you can see number of dimensions there are, you can see what type of data is it, and you can see what is the size of item. Okay, each by item size I mean what is the how much storage the item take, and then we have a size, how many number of elements there are. Is it clear? I hope this is clear. So I'll stop this recording over here. So there will be a part 2 where we'll discuss all the stuff about the operations that you can do on these numbers.